This is Physics 221, Mathematical Physics 1, and in this lesson, we're going to discuss about the cylindrical and spherical polar coordinates, and we're also going to express your vector operators in terms of these two polar coordinates. The operators we have discussed in the previous lesson, the gradient, divergence, curl, and Laplacian, have all been defined in terms of the Cartesian coordinates. But for many physical situations, other coordinates are more natural. For example, many systems, such as an isolated charge in space, have spherical symmetry, and therefore spherical polar coordinates would be the obvious choice. For a fluid flow in a pipe, your cylindrical polar coordinates are the natural choice. The physical laws governing behavior systems are often expressed in terms of the vector operators we have been discussing, and so it is necessary to be able to express these operators in these other non-Cartesian coordinates. We first consider the two most common non-Cartesian coordinates, your cylindrical and your spherical polars. Let's talk first about the cylindrical polar coordinates. Consider this point P in the figure. So this is your point P here, having Cartesian coordinates x, y, and z. So you have here some x and then y and then z to get to point P. Now, the position of this point P in space, having Cartesian coordinates x, y, z, may be expressed in terms of the cylindrical polar coordinates rho, phi, and z. Here you have your rho, phi, and then z. Your rho, this is measured from the origin. If you're going to project your point P in the xy plane, which is at this point here, your rho is measured from the origin up to where your projection of point P in the xy plane is. Okay, and then your phi is the angle measured from the positive x-axis, and then it rotates up to where your your rho is. So that is your phi. While your z, on the other hand, this is just the same z that we have in your Cartesian coordinates. If you want to express your cylindrical polar coordinates in terms of x, y, z, you can project your let's project your rho in the x-axis, and then let's project this one in the y-axis. Okay, so it has x component, which is equal to rho cosine phi with respect to phi as the angle, then your rho as your hypotenuse, and then your y you have rho sine phi. So as if you can see here, this is the opposite side of your from your angle P. So again, the position of a point P in space having Cartesian coordinates x, y, z may be expressed in terms of the cylindrical polar coordinates rho, phi, and z, where your x is equal to rho cosine phi, y is equal to rho sine phi, and then z is equal to z. Your rho, it's greater than or equal to 0, so it cannot be negative, so it has some magnitude, positive magnitude, and then your phi, this is greater than or equal to 0 and less than 2 pi, while your z is any number, but it's greater than negative infinity and less than positive infinity. So that is how your cylindrical polar coordinates look like in your XYZ axis. If you can remember in the previous lesson, we have the position vector of P written in R. You have your R in terms of your X, Y, and Z. Now, the position vector of P may be therefore written in terms of your cylindrical polar coordinates. R is equal to your rho cosine phi I plus your rho sine phi j plus your zk, or let's just say you have here your r is equal to your rho cosine phi I hat plus your rho sine phi j hat plus your zk hat. If we take the partial derivatives of r with respect to rho, phi, and z respectively, then we obtain the three vectors. So first, we get the partial derivative of r with respect to rho. Okay, so we call this one as your E of phi or E of rho. So your E of rho is equal to the partial derivative of R with respect to rho. We just take the partial derivative of this function here in terms of or with respect to rho. So you have here first, for the first term, you have cosine phi I, and then in the second term you have sine phi j, and then this one, this blows up, and then this goes to 0. Now we take the partial derivative of r with respect to phi, and we call this one as your vector e phi. So your vector e of phi is equal to uh, the negative of rho sine phi I. So we take the partial derivative of this one with respect to phi plus your partial derivative of this one with respect to phi. You have rho cosine phi j. And then lastly, we take the partial derivative of r with respect to z of this function, and this just goes to 0. This is also 0, and we have this one here. Your e of z, which is the partial derivative of r with respect to z, is just equal to your k, or your k hat. So these vectors lie in the directions of increasing rho, v, and z, but are not all of unit length. So as we said in the previous slide, the vectors e rho, e phi, and ez are not all of unit length. And although your e rho, e phi, and ez form a useful set of basis vectors in their own right, it is usual to work with the corresponding unit vectors, which are obtained by dividing each vector by its modulus, or when we say modulus again, it's the magnitude of the vectors. Now, if you remember from the previous slide, the magnitude of your E rho is 1, and the magnitude of your E phi is your rho, okay, and then the magnitude of your EZ is 1. So we divide these three vectors by the modulus or the magnitude. So you have E rho divided by 1, and then E of phi divided by rho, and then E of z divided by 1. So we get these following three unit vectors. Your E rho hat, which is equal to cosine phi I plus sine phi j, and then your E phi hat is equal to the negative sine phi I plus cosine phi j, and then your EZ hat is equal to your k. And these three unit vectors, like the Cartesian unit vectors, your I hat, j hat, and k hat, form an orthonormal triad at each point in space. That is, the basis vectors are mutually orthogonal and of unit length. So, however, unlike the fixed vectors ij and k, so as you can see here, your ij and k are fixed. The unit vectors e rho hat, e phi hat, and then your ez hat are not fixed. That is, they change in direction as p moves. So as you can see here, as p moves around here in your in your in your coordinate axis, your e rho, your e phi, and your ez also moves. Unlike compared to your ij and k, which is fixed at this directions here. We will now express the vector operators discussed in the previous lesson in terms of the cylindrical polar coordinates, or your CPC. So when we say again CPC here, we refer to as your cylindrical polar coordinates. So just a shorthand. And let us consider a vector field A, rho phi of z, and then your scalar field phi, rho phi, and z. Here we use the capital phi so that for the scalar field, to avoid confusion with the azimuthal angle phi. And what we are actually going to do here is we're going to express the vector operators discussed in the previous lesson, your divergence, your gradient curl, and then your Laplacian in terms of the cylindrical polar coordinates. We first write the vector field in terms of the basis vectors of the cylindrical polar coordinate system. So your vector field A is equal to your A rho, E rho hat plus your A phi, E phi hat plus your AZ, EZ hat. So this is just the same with the previous, wherein you have your AX, AY, and AZ in the X, Y, and Z directions. It's just here that you have your A raw, AP, and AZ, where here your AP, your A raw, AP, and AZ are the components of your basis vector, your vector field A in the raw, V, and then your Z directions. So again, you have here your vector field A, which is equal to your arrow E V hat plus A V E V hat plus your AZ EZ hat. And the expressions for your gradient, divergence, curl, and your Laplacian can then be calculated and are given below. So you have your gradient, your del of phi, the gradient of your scalar field phi, that's equal to your partial phi over partial rho e phi hat plus 1 over rho partial phi over partial phi, the smaller phi, e phi, e phi hat plus your partial rho over partial z e z hat, and then this is for your divergence. So the del dot A is equal to your 1 over rho partial uh, phi or partial rho of rho A phi, or sorry, your rho A rho plus 1 over rho partial phi of your A rho, and then plus partial uh, partial z of your AZ. And then this one here is for your curl. So you just take the determinant of this matrix here, and you get your cross product. So this is just the same with the process. It's just the same with our previous discussion. And then for your Laplacian, your del squared phi is given by this expression here. So you can pause this video for a while to examine these expressions. This is also given in the book Mathematical Methods for Physics and Engineering by K.F. Riley, Hobson, and Benz. So let us have an example. Express the vector field A equal to yzi minus yj plus xz squared k in cylindrical polar coordinates, and hence calculate its divergence. Show that the same result is obtained by evaluating the divergence in Cartesian coordinates. So our task here is first to express this vector field in terms of the cylindrical polar coordinates. After we get the cylindrical polar coordinates form of this vector field, we are going to calculate the divergence. Our third task is to show that the same result is obtained by evaluating the divergence in Cartesian coordinates. That is, we are asked to compare the divergence using the Cartesian coordinates and the divergence obtained in the cylindrical polar coordinates, and show that we get the same result whether we get the divergence of your vector field A in terms of the Cartesian coordinates or in terms of the cylindrical polar coordinates. So let's solve the problem. The basis vectors of your cylindrical polar coordinates are given by these three unit vectors here. So this is for your E raw hat plus your EV hat plus your EZ hat. But as you can see here, you have your I, J, and K. So we need to get an expression for your I, J, and K in terms of your E raw, your EV, and then your EZ hat. So what's easy here is you have for your K, so your EZ hat is just equal to K, so plus your K is equal to your EZ hat. But you need to show that you get these terms for your I and then for your J using these two terms here. So I will give it to you as an assignment to prove that indeed you have your I and J terms obtained from these two here. Okay, solving these three equations again for ij and k simultaneously, we get the following, and we're going to use this basis vectors later to substitute it in your vector field A to express it in your cylindrical polar coordinates. So we now have your basis vectors I, j, and k in terms of your E phi, E rho, and then your EZ. So this is again for your I, j, and k. And then remember that your x is equal to your rho cosine phi, your y is equal to your rho sine phi, and then your z is just still equal to z. And you're going to use these relations in your vector field A to express this one in cylindrical polar coordinates. So first you have your, we're going to substitute these relations here. So first you have your y, so you have your rho sine phi. So you have this one here, your rho sine phi, and then you still have your z. And then this one here, this is for your I. You have cosine phi e phi hot minus uh, sine phi e phi hot. Okay, so you have cosine phi e rho hot again minus sine phi e phi hot. So this is your I. And then minus your yj, so your y is rho sine phi, so you have this rho sine phi here. And then this is your j term plus your x z squared k. So you still have the same z squared, but your x is equal to rho cosine phi, and then you have your EZ hot. Okay, simplifying this expressions further, we get to the final form of your vector field A. So this is now the final form here. So you have your z rho sine phi cosine phi minus rho sine squared phi e rho hot minus z rho sine squared phi plus rho sine phi cosine phi e phi hot plus z squared rho cosine phi ez hot. Okay, so this is now the cylindrical polar coordinate expression of your vector field A, yzi minus yj plus xz squared k. Okay, so now let us take the divergence of the vector field A in terms of the cylindrical polar coordinates. And again, remember that your divergence of your del dot A is equal to this term here. So you have your 1 over rho, partial rho, rho A rho, plus 1 over rho, partial phi of your A phi, plus partial z of your AZ. So we just use this expression here, substitute these components, okay, the components of the previously expressed expression, and then we simplify, you get this answer here. This is the divergence of of your what we call this, of your vector field A. Now we are going to show that the same result is obtained by evaluating the divergence in Cartesian coordinates. So we take the divergence of this one, of the vector field in Cartesian coordinates, and if you remember, this is just your partial x of ax plus partial y ay plus partial z az, and taking the partial derivatives, you have your 2zx minus 1. And if you substitute your x, which is equal to your rho cosine phi, so you have here your rho cosine phi here, okay? So you'll see that this one and then this one are just actually the same. So you obtain the same result by evaluating the divergence in Cartesian coordinates and then taking the divergence in terms of your cylindrical polar coordinates. You just remember to always substitute after if you're going to evaluate using the Cartesian coordinates. Now let's talk about the spherical polar coordinates, and we still take the same point P in space, just like earlier. So the position of a point in space P having the Cartesian coordinates x, y, z may be expressed in terms of the spherical polar coordinates r, theta, and then phi. So here, this is the same point P. So it has components x, y, z in the Cartesian coordinates, and in spherical polar coordinates, you have your r, which is measured from the origin towards any point in space. So this is your vector r, and then your theta, it's measured from the z-axis towards your vector r, and then your phi is measured from the positive x-axis up to the projection of your vector r in the xy plane. Okay, so your phi still rotates from your z-axis. It rotates counterclockwise. And just for you to see, let's project your vector r in the z-axis. So in the z-axis, you have your r cosine theta. And then in the xy plane projection, which is this line here, this is r sine theta. So this is this same line here. This is r sine theta. And let's project this one in the x-axis. Let's also project it in the y-axis. In the x-axis, you have your r sine theta cosine phi with respect to the angle phi, and then in the y-axis, we have r sine theta sine phi, where here your r sine theta is the hypotenuse of your line projection on the xy plane. So again, the position of a point in space P having the Cartesian coordinates x, y, and z may be expressed in terms of the spherical polar coordinates r theta and p, where your x is equal to r sine theta cosine phi, y is equal to r sine theta sine phi, and z is equal to r cosine theta. Here, your r is greater than or equal to 0. Your theta is greater than or equal to 0, but it's less than or equal to pi, and then your phi is greater than or equal to 0, but it is less than 2 pi. And we do the same process as we did in the cylindrical polar coordinates, where we write the position vector of your p, and it may be written in the form you have your r is equal to r sine theta cosine phi I plus r sine theta sine phi, and then sine phi j plus r cosine theta k. So this is your x component, and then this is your y, and then this is your z component. So this is your position vector p in terms of your your r theta and then your phi. And just like earlier, if we take the partial derivatives of r with respect to r theta and phi respectively and divide each of the resulting vectors by its modulus, again, when we say your modulus, this is the magnitude of your vector. Then we obtain the unit basis vectors. You have this 3 unit basis vectors here. Okay, and we will now express the vectors or the vector operators discussed in the previous lesson, again in terms of your spherical polar coordinates. And let us consider a vector field A. So your vector field A is your r, theta, and phi, and then your scalar field phi, r, theta, and phi. And we write the vector field in terms of the basis vectors of the spherical polar coordinate system. So your vector field A is equal to your AR, ER hot plus A theta, E theta hot plus A phi, E phi hot, where your AR, A theta, and E phi are the components of your vector field A in the r, theta, and phi directions. Again, you have here your vector field A written in terms of the basis vectors of your spherical polar coordinates. Your vector field A, that's equal to your AR, ER hat plus A theta, E theta hat plus A phi, E phi hat. And the expressions of your vector operators for gradient, divergence, curl, and Laplacian can be calculated and are given below. So this is for the gradient of your scalar field phi. So you have your del phi is equal to your partial phi over partial r e phi or e r hat plus 1 over r partial phi over partial theta e theta hat plus 1 over r sine theta partial phi over partial phi e phi hat. And then this is for your divergence, your del dot A. So this is this term here. So you have your 1 over r, and you take the partial derivative with respect to r of your r squared AR plus your 1 over r sine theta, and you take the partial derivative with respect to theta of your r sine theta, and then A theta plus 1 over r sine theta partial derivative of your A phi with respect to your phi. And this is for the curl, your del cross A. So it's 1 over r squared sine theta, and then you get the determinant of this matrix, and then this is for your Laplacian. So you can pause this video to carefully examine the formulas or the expressions for your gradient, divergent, curl, and your Laplacian. Again, this is given in the book. Same book earlier, you have your mathematical methods for physics and engineering by Riley, Hobson, and Benz.